We have the joy to host and be collaborators with Nikolaos Karnesis, the speaker, who joined our local LIGO Virgo and LISA group in Aristotle University of Thessaloniki, led by Professor Nikos Terioulas. He's a postdoc since 2020, which is funded by the ESA program, program LASA-PI, developing a data analysis pipeline for the analysis of stochastic gravitational wave signals with LISA. Nikolaos graduated on 2010 from National Technical University of Athens, the SEMFE, School of Applied Mathematics and Physical Sciences. He obtained his PhD at IHE in Barcelona with title Bayesian Data Analysis for the LISA Pathfinder mission. From 2015 until 2018, he was a postdoc in the Albert Einstein Institute in Hanover. And from 2018 to 2020, he was a postdoc at APC Paris. And from 2020, he's a postdoc with Professor Nikos Terioulas. So let's start the talk. And for the questions after the talk, you can use the hand tool, since we are already 47 participants. So, Nikos, let's start the recording and you can start.
Thank you very much for this nice introduction. I'm very glad that you're giving me the opportunity to talk about this very nice experiment, this nice mission. I have to apologize in advance. Maybe there will be some discontinuities in my connection. So if something like this happens, I will try to connect as soon as possible.
Okay.
And to prevent these kind of things, I will switch off my camera now, and I will switch it back on later in order to save some bandwidth. Okay, so let's begin. I would like to, in this talk, to discuss the LISA mission. So what is LISA? What is the concept of LISA? And what is the difference to the ground-based detectors? And I will also try to summarize some, let's say, highlights of the science that we can do with LISA. And then I will jump in directly to the data analysis challenges that we're going to face that are quite different from what we are used to with the LIGO Virgo detectors and data. And I will also advertise the work that we do here in the Aristotle University with collaborators. So let me quickly begin with what we have now. Let's start with basically what is the effect of gravitational waves of passing gravitational waves. If we assume that if we let's say put some if we create a ring of particles, some test particles that will form a ring, for example, and then if there is a passing gravitational waves from them perpendicular to the screen, we will see them oscillating with this way. So this is the effect of a passing gravitational wave, which is predicted from GR. And this is exactly what we use if we want to detect them. So we build large detectors which have the shape of L. And this is what the LIGO detectors are, for example, in a picture here. And we put test masses at the ends of these huge arms. These test masses in this particular case are huge mirrors, which they basically are used to reflect light. So we shoot light from the center of this experiment, and the laser bounces to the detectors, and then the beams are combined back in the beginning. So if there is no passing gravitational waves, then the laser beams, the light is going to the two laser beams combined in the end will give us zero. So one beam will cancel the other, so we'll measure nothing in the light detector in the end. But when there is a gravitational wave passing through this detector, through this antenna, so the arms will start oscillating. And from these small oscillations, we will read out the non-cancellation of the light at the photodetector. So this is the best way we have to detect gravitational waves, and it works. So there has been previous attempts, but this is, as we have seen, we have managed to detect it some years ago, and now we're doing it even better. So how does the waveform looks like? How does the signal looks like? So we have here the different stages of an spiral of two large masses that oscillate one another, and when they coalesce, and then some point they fall one onto another, we have merger, and then some ring down. And this is the time series of the event as measured by the two LIGO detectors, one in blue and one in orange. And you can clearly see the correspondence of the waveform to the spiral of these objects. So since 2015, there has been, when there was a first detection, if I remember correctly, there has been a lot of other events measured by the network of ground-based detectors. And here is, for example, this bank, let's say, this event bank, this from black hole binaries, and we can see the waveforms here. These are the time series of the waveforms, and on these left panels we see the spectrogram of the signal, so time and frequency, and we see that the characteristic shape that they take, this whooping kind of signal. So it's and if we translate it into sound, it will do this kind of whooping sound that people have been advertising since the detection. So here on the left, we see how well we can localize all these sources, and it's quite evident that with a couple of detectors online, or three of them, we cannot do so localize so well. So I mean, but still, for some long-lived events like this one here, we can have good localization. And this depends on where the detectors are, how the detectors are distributed on the Earth, etc. So having said that, in the future, we expect more detectors to be operational. We have Kagra and LIGO India. If I'm not mistaken, I think Kagra is already is able to gather data, but I don't know about its sensitivity. But we can expect that in the 2030s, we will have LIGO India, and there is also development for the Einstein telescope, which will measure gravitational waves in a little bit different band than the others. So there's going to be a lot of developments in the future, and this catalog of sources here is this catalog of sources detected so far with the corresponding error bars on some of the characteristics parameters, these violin plots. We have, for example, the mass of the first object, mass of the second object, the mass ratio, the effective spin, and the luminosity distance, just listed here as an example. So this is all very nice, but I have added here what we see is, let's say, an overview, let's say, summary of the noise budget of the LIGO detectors, let's say, and with different colors, what we see is the different noise contributions to the overall budget, and the measured noise, the total measured noise for O3, which was the most recent run, is shown in blue. So this is the total thing that let's say the amplitude, the noise amplitude of the signal at different frequencies. Let's see, and we can see with different lines the different models of the environmental noises, and you can see that in lower frequencies we are pretty let's say constrained by thermal noises and seismic noises and all these environmental noises that come from the environment of the Earth in general, because these detectors are located on the surface of the Earth, and the Earth is shaking all the time. So even if we are able with various techniques to mitigate for these noises, it's quite hard to push to lower frequencies than 10 hertz here. So this is kind of a hard limit, let's say. So if we want to measure events, let's say with higher masses, which means that the they are producing signals in lower frequencies, we have to do something else, build other detectors, or simply try to go into space. So in space, all these environmental effects are not there. It's a very quiet environment. So we could take basically a ground-based detector like a LIGO and put it into space. This is the main idea behind the LISA mission, the Laser Interferometer Space Antenna, right? But it's, as you will see, it differs quite a lot than the ground-based detectors, because it's different in the sense that it's not in the ground. That's because, I mean, this is a huge difference. We cannot, as soon as it flies, you cannot send people to fix things or align objects, align components on the optical benches or anything like this. So as soon as you launch it, that's it. And the data bandwidth is different. It's in space, it's far away. So we have to choose which data we want to download on ground. And of course, since we're talking about different sensitivity spectrum, different frequencies, will have different signals populating the data streams. So let's look a little bit in more detail. What is LISA? LISA is a constellation of 3 spacecrafts and each spacecraft hosts a couple of test masses inside it. That they are free floating. They're in free fall conditions, right? They do not touch the walls of their enclosing. And what happens is that we shoot laser from one spacecraft to the other. This is 2.5 million kilometers. This is quite far away. And then the laser bounces on the test mass on the other spacecraft, coming back, and then back and forth. And basically what we do is we build 3 virtual interferometers. One is this one is this one, and the other is that way. So we call this the XYZ, let's say, outputs. The orbits of LISA is going to follow the Earth, as we see in this cartoon here, about 20 degrees behind Earth. And it's a heliocentric orbit, of course, and it's going to rotate as it rotates around its orbit around the sun. So this is how it's designed. I'd like to maybe this is some short history about LISA, but it's not very important now. Just to say that the idea is not recent. The idea of LISA exists since many decades, and there have been a lot of effort in getting this idea out. There was in 2011 or 10 when I started my PhD. The NASA backed from their funding, so there has been to be changes from LISA and all these kind of things. But the recent gravitational wave detection and the success of the LISA Pathfinder mission changed everything, and then everybody was on board again. That's I guess the main points of the history of LISA. Now we are in the phase A of the mission. Phase A is finishing now, and we are well into the development of it. A little bit on the measuring principles. I have what this cartoon is showing here, how we measure, and you will see immediately the differences to the ground-based detectors. So here we have the strain amplitude, the signal, let's say nature, from orbiting binaries. And then what we have a peculiar response of the instrument, because the instrument is sensitive, of course, to the axis, is very sensitive to the axis perpendicular to this triangle, right? And this triangle of this formation, this constellation, is rotating, and at the same time is in orbit around the sun. So one big difference is the response. And then we have the phase readout. We read the output of the lasers, right? The phases, which then we combine on ground. Now, what I would say, the big difference to ground-based detectors is that this triangle, this constellation, is floating in space. It's not fixed on the ground. So this distance of 2.5 million kilometers, is wobbling. So it's changing slowly. And for that reason, we have to perform is called the time-delayed interferometer algorithm, which is basically you take the phase readouts that are on ground. These are, if you try to get gravitational waves from these readouts, you will see nothing. There is orders of magnitude of noise, of laser noise. So in order to cancel the laser noise, we have to artificially shift, delay the time series and combine them together in order to get rid of this noise. And we get these delays from the position of the spacecraft themselves, right? So then we have this combination of X, Y, and Z channels. We have plotted here the output in gray. These are the three. They have potentially, I mean, hopefully the same kind of levels of noise. This simplifies, in this simplified scenario, for example, if they have the same level of noise, they all overlap on one another. I have plotted the power spectral density of it. And what we usually do if we want to do analysis is we linearly combine these raw outputs, in a sense, to form these noise orthogonal channels, A and T, A, E, and T. You will see them in red and in pink here, where if you assume that the changes of the length of the arms are very small, they can be assumed to be noise orthogonal. So all this, the noise covariance matrix is diagonal, and it greatly simplifies the analysis. And you have this channel where the gravitational wave is greatly suppressed, so we can use this for calibration purposes. Just to show the instrument, how it looks, how it will look like. We have the two telescopes. This is the main instrument on board one of the satellites. We have the two telescopes shooting, pointing to the other two satellites, and we have the optical bench here in this cross section. This is perpendicular to the telescopes, where we are basically gathering the light, and then we basically measure the distance to the test mass, which is enclosed in this orange enclosure here. In detail, you'll see how in this figure here, which is from LISA Pathfinder, how the test mass is enclosed in this caging, and how it's basically a vacuum enclosure, and we try to control it at some degrees of freedom, so it doesn't touch the housing in any case. Otherwise, we will not be able to measure anything. So as you can imagine, this is a pretty big experiment. Shooting lasers into 2.5 million kilometers across the sky is a big, let's say it can be optimistic, and so it's quite hard to achieve this technologically. That's why in the late 90s, this LISA Pathfinder mission was started to be developed by ESA. And what happens is that you just take the two test masses, put them into their enclosure, and then try to measure the relative acceleration between them via means of laser interferometry. So basically what happens is you take one LISA arm, and from 2.5 million kilometers, you shrink it down to a few centimeters. And what you do is you try to measure if the environmental noises inside the satellite will allow you to measure the position or the acceleration of these test masses with this accuracy required to measure gravitational waves. If you cannot confine and model at least the noises inside the satellite, then there is no way that you could do it to find 2.5 million kilometers apart. So the great result of LISA Pathfinder, what you see here is the power spectral density of the noise of a single test mass. This is frequency, this is the noise power spectral density. And with blue, you see the data as measured by LISA Pathfinder. And with red, you see the requirements for LISA. So even for a technology demonstration mission, we have managed to surpass to the requirements for LISA Pathfinder that was set. This was quite above, and even measure something that is better than the requirements for LISA. So even from this, from the beginning, there was a lot of the mission was. We can say that it was, let's say, successful. All right. So these are great news, and they came at the same time where the gravitational waves were detected, and this put the LISA consortium together and started pushing for the mission. Right now we have an L3 class mission that it's being developed. So what is the science with LISA? I will try to highlight some key aspects of science. This is the main plot that basically summarizes what we are going to measure with this instrument. What we see here is the characteristic strain, which is basically the output of the interferometer deconvolved by the antenna response, let's say. And in frequency, we already see that we are in much lower frequency than ground-based detectors. The sensitivity of ground-based detectors starts at 10 Hertz around here, as we saw before. So we have a few types of sources. The most notable ones, the first thing that we see is these type of signals, which are massive black hole binaries. And these will be one of we expect the rate of these signals will be a few, let's say, per month to a few per year. And they will appear in the LISA band, let's say, from quite early. So we will basically be able to measure a lot of cycles of them with quite high signal to noise ratio. So it's one of the very interesting signals that we will see. Then the second striking signal, let's say one of the also most important things that we'll see is this weird, let's say, noise of particles that we see here. They are the galactic binaries, as we call them. These are ultra compact binaries that are located in our galactic neighborhood. These are mostly basically white dwarf binaries that they are where their orbits are not developed, are not evolving, do not evolve for the duration of the mission of LISA. So they appear to be like monochromatic most of the time. So there are going to be millions of them, with a few thousands of them with high SNR. So we will be able to get them out of the data. They are also a source of noise of LISA, but I will say a little bit more about this later. Then we have the extreme mass ratio in spirals. These are objects, binaries, where the mass ratio is extremely small. So one object is orders of magnitude heavier than the other. And this will give us all these very nice, weird and nice harmonics in their signal. They have all these peculiar orbits. And then we have the lighter types of black holes, the ones that LIGO and Virgo are detecting. So for these are depicted with these lines here. Why? So for some of them, they will not, their orbits will not evolve for the duration of the LISA mission. So they will appear at the same almost frequency as the galactic binaries, as monochromatic sources. But some of them, they will start evolve, so they will come closer to one another, and they will start traveling in frequency, and they will fall directly into the bands of ground-based detectors. So these are also very interesting types of sources. So let's look at them. Let's take a look a little bit in more details. First, for the black hole binaries, the massive ones that we saw. So they have 10 to the 6 to 10 to the 9 solar masses, and they will be detectable with quite high SNRs, sometimes in the order of thousands. Here I have plotted a few waveforms from different population models, just to have this, to see how they look like in these TDI output channels. And here they are the time series of a particular source of that is plotted. I think this was a few hundreds of SNR. But what we can see is that the signals really, of course, are pretty similar to what we see in ground-based detectors, just shifted in low frequencies. We're not talking about milliseconds here, but in minutes and hours, etc. I think I have an exponent missing here in terms of seconds. 10 to the 7 should right here. So these are our equivalent whooping events. In LISA, like LIGO has these small whooping events, we have these in shifted in lower frequencies. These are the most short-lived signals that we expect to see in LISA. And it's quite interesting that at some population models, some seeds, let's say they predict that we are going to have like so many of them And some of them will be sub-threshold events, so they have quite few SNR. So we will have a popcorn kind of noise in the background always as LISA is flying. So this is something that we are looking with Daniel Langirudi, who is a student of Elena Rossi. And but it's very interesting because this adds to the astrophysical foregrounds that we measure with this mission. And then we can move to the lighter objects, let's say to the stellar origin black hole binaries, the ones that ground-based detectors see. So for these guys, we hope to see a few of them, but there is still not. I mean, if we extrapolate the population that we see in the ground-based detectors down to a few to the frequency range of LISA, we can see that we can basically predict that these signals will be a lot of them, but not many of them will have a high signal-to-noise ratio. So we will have to dig into the noise and really search for them. But they will generate a confusion type of signal, as we see here in this plot. So this is a DDI output channel. This is the noise of the instrument in gray and dust black. And here we see the confusion signal that is being generated by this type of sources. So this bump here it's because of the response of the instrument. Generally, it will create something like a power law, as we expect. So yeah, I mean, and here this is a histogram of the sources that we will recover if we assume different SNR thresholds for their detection. For example, if I say that I can dig out of the signal of the data signals that have SNR equal to 5, I will get 65 of them. But if I need higher SNR to get them out, then I will basically get nothing. So we are trying to study now with people from the University of Stavanger to do this simulation properly by numerically computing the stochastic signal by computing its waveform, simulating catalogs, and then computing its waveform and adding it into the data stream to see how many of them will be realistically detectable and what is the confusion signal that is being generated in the LISA. So the method that we use for this type of analysis is already published a few weeks ago. It's already put into archive. So there is a lot of things that we can do with these objects. We have seen that there are stroke signals, they evolve inside the LISA band. So by measuring a good number of them, we can study their formation mechanism, their seeds, the population, and everything. And we can use them as accurate distance. We can basically do accurate distance measurements, use them as they call them, standard sirens. Because what we basically get for free, let's say in quotation, when we measure gravitational waves, we get the luminosity distance with very good accuracy. So for the massive black hole binaries, we will get pretty good accuracy, in some cases less than 1%. And we measure these guys for very high redshifts. So if we also measure Z from the electromagnetic counterparts from these sources, we will have we could try to do some estimate of the H0 of the Hubble constant, let's say. And this is what has been already tried before with a single event of the LIGO detector, LIGO-Virgo detection, where there was an electromagnetic counterpart. You can see here the values of H0 and how it's estimated by different by Planck and Suze in green and orange, and what is the PDF of H0 if you assume the measurement of gravitational waves. So this can be done. We can do the same thing with LISA and the massive black hole binaries that we are going to measure. Now, the same applies to the lighter ones, but of course, provided that we measure them. But now there is also the good thing about these guys is that if we measure them, there is the possibility of multiband detection, which is really interesting and and it's worth looking at this idea. So basically, what LISA will provide is a warning in terms of hours and months or months before a particular source travels from its band down to LIGO detectors. So what happens is that we measure different parts of the waveforms. The two detectors measure different parts, and then what you basically can do is you can measure some parameters better. For example, for the chirp mass and the total mass, here you see this error ellipsoid by assuming different detectors, right? For LISA, you see that you get pretty big error for the total mass, but smaller error on chirp mass. And if you combine with a ground-based detector, so in this example, it's the ET in Cosmic Explorer, you will get the green, this green ellipsoid here, which is really better than using its detector separately. Okay, so ultra-compact binaries. Here I have put an example, a more clear example of what in the TDI output, how the signal will look like of the galaxy. And it's this blue signal here, and you see all these spiky lines. All these are the sources that we were discussing before. They have very short periods, and they are almost monochromatic. Sometimes if we measure for, let's say, 6 or 10 years, we will measure the change of in their orbits, their F dot, let's say, but for not many of them. We will have millions of them in the band, but and they will create a type of confusion, let's say, noise, because we will not be able to separate all of them. We'll get only a few thousands, and the rest of them will create this cocktail party kind of problem. Too many sources occupying the same frequency beam, and then they all have quite low SNR, so it's going to be quite difficult to dig them out. But this is an astrophysical foreground that is going to be it's going to be guaranteed. It's a guaranteed detection, let's say. So these compact galactic binaries are going to be multi-messenger laboratories. We can, after LISA detection, there are going to be electromagnetic follow-ups, and because LISA is going to measure their position with pretty high accuracy, so we can test models of their evolution, mass transfer, and accretion, and all these kind of things. And one of the nice things of the nice applications we can do is that we can use these well-localized binaries to infer the structure of the Milky Way. So this has been studied in detail by Valeria Korol in this nice work, but also we have an example with, for example, one of these example project is the project of the thesis of Mary Georgousi, who is an undergrad in the Aristotle University. So what we do in collaboration with Valeria Korol and Mauro Peroni, Mauro is in Imperial right now and Valeria is in Birmingham. So we study basically how the shape of this confusion noise that will appear in LISA band, and we try to measure it and to model it and connect it to the different to infer the total mass of the galaxy and the shape of it, basically. So for different seeds, so for different scenarios of sources, we basically use this population synthesis code and then produce catalogs where we then produce the signal into the LISA band, and then we check what will be the confusion noise. Then we fit, let's say, an empirical model of it, and then we connect the parameters that we fit here. This is not very important, just so these parameters for this empirical model. And we want to connect these parameters to the actual properties of the galaxy. This is a very interesting and nice project that is currently ongoing. Another thing is that there is a possibility of measuring, detecting exoplanets with these guys, because of these, they have these monochromatic type of waveforms. If there is an orbiting, let's say, large planet or brown dwarf or whatever, orbiting around this binary, the waveform will be quite different. And this is work that this was predicted by Kamila Danielski a few years ago. And now we're working on making more accurate parameter estimation on how to get these type of signals out of the thousands of objects that we would detect with LISA. And also we are talking about the 2030s, right? So there's going to be, if LISA flies in 2035 or 33 to 35, there's going to be a few years, 1 year, let's say, until it starts operations. And so there's going to be a lot more surveys and a lot of missions looking for electromagnetic counterparts. So we expect this to be a great opportunity to, we'll have also more instruments looking at the same things. So it's a little bit, it's exciting, let's say, with this in the aspect of multi-messenger astronomy. Finally, we have the cosmological sources. So these are some theories predict that we will have some kind of stochastic signal due to processing in the early universe. Here in this plot, you see the omega gravitational waves in frequency, and you see that if you go back to very low frequency, some of these theories, they predict signals that could be measured by LISA. Here is, for example, LISA and LIGO and all these experiments, the sensitivity of these experiments. So we expect this. We expect LISA to be sensitive to these signals. We just have to dig it out of the noise. So this is a heavy task, because we basically will not know exactly also the noise of the instrument. So there is going to be a lot of techniques to try to dig it out. I think we can skip this. This is just too technical to advertise the analysis of these type of signals, but we can leave it for later. And then we have, of course, the unmodeled or unforeseen sources. We enter the era of exploration. So in these frequencies, there are going to be unexpected things, and we have to model them as well and try to be ready. So the final part, I'd like to focus on the data analysis a little bit of the mission. As you have probably have guessed, since if you have been looking at this type of signals that will go into the LISA band, so we will have, as soon as we start operations, we will have everything inside the data at the same time. So this is one of the major differences to ground-based detectors. So we start operations and we have galactic binaries, we have strong massive black hole binaries, lighter black hole binaries, and everything, all unmodeled sources, all in the data stream. So this is taken as an example from the second LISA data challenge, if you want to take a look. And apart from this, don't forget that we will have also the instrumental noises. So noise is not going to be perfect. We will have gaps, we will have instrumental glitches and everything, and or Gaussian bursts or whatever. And then this even complicates things, matters even more. So there's a lot of effort, there's a lot of weight in the data analysis of these of the signals for LISA. And this is what the scheme of analysis that we have been discussing the last years. So we have invented this kind of cartwheel, right, of analysis. We have every day we'll get more data, or every day of two, and then we will have to analyze them. So the first thing to dig out will be the compact galactic binaries, because of their number and their strong signals. So we will try to get as many as possible out of the data, and then we pass the residuals to the next part of the wheel, which is the looking for massive black hole binaries. At the same time, we have to take care of the noise model and the instrument model, because LISA is rotating, LISA is not rigid, and the noise is fluctuating due to thermal noises, due to the orbits or whatever. So we have to always calibrate the instrument. And then we pass residuals to the lighter black holes, update the instrument, unmodeled sources, update the instrument. We're looking for embries, update the instrument, and finally, if we have searched for everything and we are confident that there is only stochastic signals, we can try to look for cosmological or other astrophysical foregrounds here. So this will happen until the end of the mission in the same way as in the Gaia, where then we plan to release catalogs of sources, let's say every X years, or I don't know, all these things are under discussion here. So in this context, we have this project proposed to ESA, and it's being funded. We call it LISA Pi. It's sort from the LISA pipeline for stochastic signals, and this involves the LISA group at the Aristotle University. These are the members. They were not so many, but let's hope that we grow larger. So let me explain what we try to do with LISA Pi. We basically try to contribute to the data analysis by proposing, let's say, statistical algorithms to look for these kind of signals. Let's start a little bit. I guess people that have been working on this already know what the Markov chain Monte Carlo is, but I will try to. I wanted to show the basic principle. So if we have some data stream D, which is the instrument noise contains the instrument noise and the signal that depends on a set of parameters theta, then we can assume that if the noise is Gaussian, that we can build the Gaussian likelihood for the signal, right? And then we make the posterior distribution of the parameters by assuming also by defining a prior for these parameters, and we try to estimate which parameters maximize the posterior, let's say. Oops, excuse me. So these brackets here represent the noise weight and in the products. Basically, if you take 2 time series A and B, it's the FFT of them squared divided by the power spectral density of the noise. So it's it's whitened data, basically, right? So then what you do if you have built the posterior, then what you do is you want to sample it. So taking this video, you start by a point, you propose another one in the parameter space by given a proposal distribution. And if you compare the posterior at a given point with a previous point, and then you accept it or reject it, you decide to accept it or reject it based on some probability. And then you build the posterior probability of this parameter theta after a few thousands of iterations. So this is a basic concept, and it's very useful when the posterior surfaces are bumpy. So when you have too many sources, when you have low SNR sources, then this is a good method to get the parameters out of the data, but it's, as expected, a little bit slow. So this is the same happens if you basically want to dig to look for signals, but you don't know how many components they are. In the example of the galactic binaries, we know that there are a lot of them. We know the model for each one of them, but then we do not know how many it's in the data. So we basically use this, as it's called, the reversible jump Markov chain Monte Carlo, which is a generalization. In this example here, you jump from a single dimension Gaussian, for example, if you imagine that this is the posterior, and then you add another source in the data. So you jump in the 2D posterior, and then you come back. So, but these type of algorithms are slow and also can be challenging to tune. They do not work out of the box. They are not black boxes that you throw them data in and then you get the results out. You have to make sure that they are efficient in sampling. And this is let's say a tuning problem that it's always there. So this idea is not new. Tyson Lindenberg et al. And Neil Cornish et al. Have been working on these ideas for years, and they have applied it already for the compact galactic binaries for LISA. But they're focusing on making the sampler more efficient in terms of defining proper priors and good proposal distributions. What we want to do with this project is to propose to make the sampler better itself. And if you combine it with their improvements, you have a very efficient sampling algorithm. So the first thing that we did is we implemented what is called adaptive parallel tempering, but now for reversible jump. If you can imagine that this is the posterior, this is a shape, let's say, for the posterior, and this is the parameter space. You basically have temperatures that it's where this basically means that you multiply your posterior with a small number. And then if you have high temperature, this means that the posterior is going to be a little bit, it looks like it's melting, right? So all these big peaks are being eliminated almost, and it's higher to go from one place on the other. So it's easier to sample the posterior probabilities, even if you have changing dimensionality as in the reversible jump. And then what happens is that you run parallel chains you run parallel chains exploring the number of models and and their parameters in different temperatures. And what you do for this, you get them to talk at some point and they exchange information. And this is a good way to quickly dig out parameters and sources out of the noise very fast. So this is already implemented, and I can show you in this very small cartoon how it works. So in this toy data set, we have this blue data here, and we try to get out how many peaks are in the data. Green is the true one. We have a mixture of Gaussian and Cauchy distributions, and here you see the MC chains, how they evolve. For the Gaussian ones, the algorithm managed to find them quite well. They are pretty bright, but these guys, they could be approximated either by one or by two or by many Cauchy distributions. So you see how it evolves in time. The same applies to galactic binaries, but it's not, let's say, a 4-parameter problem now. Each of the binary has 8 or 7 parameters, so it's a little bit more difficult to do the same, let's say. This is an example of the output of the code. I don't think it's we can go into it. For example, these are the chains of the temperature, how they evolve in time to maximize the information exchange between the different chains. And here is the change of the dimensionality of the problem. So the cold chain is depicted in black, and you see how it tries to sample the correct distribution in K, how many components are in the data, 3, 4, 5, etc. So higher let's say change with higher temperatures, they're exploring more aggressively the whole hyperparameter space, let's say. And this is one of the good aspects of this code that we have developed. And it works. So we have tested it with a few galactic binaries. This is a very small narrow strip of the LISA band that we have put this into play. But it's getting already slow. So this is okay for prototyping, but it's getting harder and harder the more sources we add in the data. That's why we have plans to do several improvements. With Natalia Korsakova from CIRTE, who is an expert in machine learning at all these kind of things, we want to use neural networks to build efficient proposal distributions beforehand, before starting this algorithm. And this is a very nice idea that we're discussing. And then with Michael Katz, we want to migrate to GPU computations, because this will really untie our hands in terms of prototyping and efficiency. And finally, this ELISA Pi is part of the of a collaboration that is going to participate to the second ELISA Data Challenge to basically dig out the data. This is a collaboration with people from the AI in Potsdam. This is us from the APC Paris and Birmingham and Caltech. So a few people gathered to join forces to analyze the different types of sources that are there and simultaneously. I think I'm well over the hour. So let me just say a little bit about data challenges. Is we produce data from realistic, let's say, a realistic instrument. We have good simulations of the instrument, and we choose different nature scenarios, right? So the first ELISA Data Challenge called Radler is already completed, and it was quite successful. We are now writing publications about the analysis that was performed. And now we are running the second one, which is called Sangria, where there are a few flavors of it, yours and Spritz, that they have different components, like a more noisy instrument or different types of weird sources inside. You can find data in this link here, and I welcome everyone to try to even try to dig out sources from data. I don't know why people started naming them after alcoholic beverages, but I guess everybody needs one in this time of the year. So yeah, to conclude, I'd like to say that ELISA is well underway, and the community is growing. There is a lot of projects concerning both science, instrumentation, and data analysis, and there is a lot of weight in the data analysis. because of the particular nature of the instrument. So a lot of side projects that we have also in the Aristotle University, for example, we study the gaps, how the gaps of the data affect the parameter estimation of massive black hole binaries, because there's going to be a lot of gaps. We expect, unfortunately, to have some gaps in the data. And there is going to be a paper in archive from Friday about this. And then we basically transfer the know-how from LISA Pathfinder. We had some glitches and noise artifacts in LISA Pathfinder, and we plug them into the LISA simulator and see how this complicates things. Then we work on the global fit and etc. So more things are to come in the meantime, and I will finish saying that this is a very nice community, and it's a welcoming one. It's still on the first steps, but I have been really enjoying working within the LISA community. So I'll stop here, and I will be happy to take any questions if there are any.